Hello, welcome to the Sunday Science Q&A. I'm Robert Ince. You're about to meet very shortly Helen Czerski, who does this every week as well, and sometimes with, something's just fallen off the desk. Did you hear that? I don't know. Anyway, it's chaos here, which is annoying because if we were actually doing chaos theory or something about entropy, but in some ways we are because we're doing material science and sometimes things do fall apart. One of our guests, Mark Miodownik, I did some very serious scientific research with dealing with oobleck. So, that may well be coming up again. In fact, it's a fun thing to do today. If you've got not much else to do, making oobleck is always an absolute joy. And we're also joined by Suze Kundu as well. We'll be meeting all of them very shortly. Say hello to Trent's given me a note to say Happy Mother's Day. So I'm going to say Happy Mother's Day. I hope you're all doing okay. And remember, use your brain well. Remember, the reason that birth can be such an agonizing thing is due to the great big size of our skulls. So if at any point you decide to misuse your mind and your brain and not use it for curiosity, empathy and wonder, then in many ways you're being extremely rude to the sometimes very ugly birth process that may well have been involved. There we go. That's the instructions out of the way. Don't forget you can support us via Patreon. That will be very, very useful because it's entering the second year of having no live work, which is kind of how I make a living. So it'd be nice if you can, but it doesn't matter if you can't. We always make things for free as well. Book Shambles every week. In fact, I should say that it's well worth listening to this week's Book Shambles because Nell Frizzell and Josie Long have a particularly interesting conversation about Nell's latest book, which is dealing with ideas of motherhood and some of the conflicts involved in that and many of the different sides to it. So listen to our Book Shambles. And also the current Uncanny Hour is the second part of our John Carpenter show, which is Stuart Lee and Alan Moore and Priya Natrajan and Clara Nellist and Reece Shearsmith and loads more talking about In the Mouth of Madness and also about Prince of Darkness and John Carpenter generally. And this week, the one coming up very soon is all about Derek Jarman and Jubilee, and that's with Richard O'Brien and Toya Wilcox and plenty of other people. He's given me too many things to talk about, so we'll mention some of the other things later on. Also, if you do want to ask any live questions, then you can just either leave them under the live chat or just tweet them to @CosmicShambles, and we will try and deal with this. We've got a huge number of questions in already, and I think it's going to be a lot of fun. Oh, and I will mention it. Next week, our guest is Nicole Stott, who is fantastic, who engineer, who also then became an astronaut and now does fantastic work mixing art and science to get children increasingly excited by the idea of space exploration and scientific ideas as a whole, which is not a bad job, actually, because you're starting from a good place when you say, hey, kids, do you like space exploration? Fortunately, many of them do. So let's start off with you, Helen. You have a day in science for us. Give us our history lecture.
I have a couple of things just to follow on from that. One is that it is true that making oobleck is an absolute joy, but we have to add that clearing it up afterwards is a deep and miserable nightmare. So I encourage everyone who wants to have a go, but definitely do it somewhere where the tidying up is going to be okay, because otherwise we're going to get tweets. Also, it's Pi Day. Happy Pi Day. It's the 14th of March, 314, if you write your dates that way around. And so those are the first three digits of pi. So it's Pi Day, and we can all annoy Matt Parker by celebrating Pi Day and not Tau Day, which is twice the same number, because physicists write 2 pi a lot. Anyway, this week in history, 40 years ago, in 1981, Robert Axelrod published a paper which became very famous in lots of different areas, and the title was The Evolution of Cooperation. And you've probably heard of it. There was a book that he wrote a couple of years later. I was actually just looking for my copy of it, couldn't find it, but I remember reading that book, and even though I wasn't a biologist, it was really it made a lot of things clear. And the reason that this book was important is that up until that point, the concept of evolution had sort of the models of it, the theory, it had a problem with cooperative altruistic behavior when people just help other people just because. And because, in the model of the selfish gene, the gene looks after itself. Why would it bother with anyone else? And so what Axelrod and his collaborators did was to really dig into mathematical models that showed that if you even had a little bit of cooperative behavior, it would grow and it would spread and it was stable in the population. And so it turns out that we aren't all miserable, nasty beings who are naturally selfish, entirely selfish, but that cooperation is actually very common. It's a very, very useful strategy in evolution, and it is consistent with evolutionary models. And of course, that then went into a whole load of psychology. And I think it's the most cited paper in Political Science, because apparently political science people need convincing that you have to be nice. So that was this paper 40 years ago, which really opened up the idea of cooperation being a fundamental part of how evolution works.
Brilliant. And next week, I'm excited by, we won't say anything, but you have some brilliant, exciting footage for our engineering conversation next week, don't you?
Yes.
Magnificent.
Cannot say any more about it. It's very, very big. Yeah.
So I will mention, if you've got, as I said, Nicole Stott's going to be on, feel free to ask your questions about space exploration, etc. But also remember, she spent a long period of time also as an engineer as well. And so if you have questions about engineering, we're going to be, I always say we're going to be covering it. We're not. Helen is, and Nicole is, and I'm going to go, I don't know. So, Suze, it's great to have you here. You are now let's just get, because nanochemistry, and the idea being that this still feels for a lot of people a tremendously kind of contemporary world of science, a contemporary world of understanding. So before I get to your show and tell, just for those who aren't quite sure what nanochemistry is, what is that the study of?
So nanoscience is, generally speaking, the study of materials that, at least in one dimension, fall within the nanometer scale. So a nanometer is 1/1000th of a meter, which is very, very small. We can't see it with the naked eye, but we do often see kind of the effects of nanotechnology and nanostructures. For example, I think a lot of people have that adorable fun fact about butterflies that look blue, not actually being pigmented with blue pigments. It's actually a process known as structural coloration, and it's because the tiny structures on those butterfly wings are within that nanometer range, and so they interact with light in a very specific way. They reflect light back in a very specific way. So it's not a pigment that's reflecting the blue light back. It's actually these tiny nanostructures interacting with light. So nanochemistry and nanomaterial science is effectively this big giant quest to see what we can tweak on that teeny tiny scale to make changes on the macro scale that we can utilize to solve all of the problems around us. It could be energy, it could be medicine delivery, it could be any of those things. And it's a lot of fun as well.
Brilliant. Thank you very much. That's an excellent summary. Now, what is your show and tell? I hope it is something magnificent with the butterfly that you've made at home.
I mean, it should be, and it should be as epic as that. But I've kind of taken a bit of a zoom out, and I've gone for material science more generally. I have a bit of a theme, I think, if you've been to some of the 9 Lessons shows, or if you've seen me on one of your lovely Cosmic Shambles shows before, you'll know that I love experiments that I can eat. So my show and tell today, I'll go for the slightly less sticky version, is one of these. So this is a Cadburys Cream Egg. This is a UK Cadburys Cream Egg, and they're 50 this year. They existed ever so slightly before 1971 in a slightly different format with a slightly different name, but they are celebrating their, wait for it, marketing people, well done with this, their 50th. So it's their golden goobly, because a cream egg is known for its very, very gooey insides. Now, there's lots and lots of discussion all the time. Not all the time. Maybe I hang around in particular circles where we chat about the nerdiness of chocolate and science that we can eat. But there's a lot of discussion about how they're made. A lot of people think that perhaps there's a solid shell and they inject this gooey fondant inside it. Other people think that the fondant starts off as a solid, and they have some kind of enzyme in it that over time turns it from a solid into a gooier structure. In actual reality, cream eggs are made in 2 halves. So you have one half like this, and the other half, which is slightly less yellow in the middle. Now, the way that they create this is actually really interesting, because cream eggs are actually made entirely liquid. So chocolate is kind of extruded into these molds. So you have this chocolate half of an egg. And then the liquid fondant goes in on top. So you have the white fondant, and then on one side you have this orangey yellow fondant so that it mimics an actual egg. It all starts liquid. So how do these things not mix together as it all sets and as it kind of closes up to form a whole Cadbury's cream egg? Well, it's actually down to just one of the most basic material properties that we think about, which is density. So the chocolate and the white fondant and the orangey yellow fondant all have slightly different densities, which means that they don't mix up with each other. So as the egg is cooling down, you get this beautiful shell, which used to be more chocolatey than it actually is. So you can send all your complaints to Kraft and than all of those people, and not me, because I didn't change it. And you get the delicious chocolatey-ish shell and the delicious fondant inside. It is delicious, it is amazing, but it's also effectively kind of pure sugar as well. So eat these at your peril, everything in moderation, but just a little bit of pre-Easter science for you today.
And next week, we'll have you back on to say how they put the little bit of chocolate inside the chocolate eclairs toffees.
Hell yeah.
Which, of course, I can't eat now because I'm 52. And frankly, these teeth are not even meant to still be in a living creature anymore. But that's something Kurt Vonnegut once told me about. Well, didn't tell me about. I mean, I read it in a book, but I count it as a personal relationship. Also, remind you, because cream eggs were mentioned there, that we're also on Easter Sunday, and we'll have Brian Green on Easter Sunday. So next week, Nicole Stark, week after that, Brian Green. Mark, the Oobleck Master. I've enjoyed you. What is your show and tell today?
I'm going to talk about animate materials. I've been talking about it all week. You know, it's hard to stop me once I get going. Everyone. Sorry, apologies about that. Do you want to tell you now about them, or do you want to do some preamble? I thought I could do some preamble about Oobleck and how messy it is. I've got a tip for you. If you want to make Oobleck, all you need is some corn flour, and when we made it, Robin, we kind of dyed it lime green, didn't we, to kind of fit in with the Dr. Seuss Oobleck. But you can make it any colour you want with food colouring. And then it's all about adding just the right amount of water. I would use a little pipette or a little droplet. And then at some point, it goes from being this sort of just normal stuff into a strange, odd stuff where if you poke it fast enough, it becomes a solid and cracks up. And if you just stir it very slowly, it's a liquid. And if you walk away from it and turn back really quickly, sometimes you think it's moved, but it usually hasn't. Sometimes it does, though, or it drips onto the floor. It gets very messy, as Helen was saying, because it's so much fun and you want to make more and more of it. And the tip I've got, sorry, this preamble's got longer than I thought it was going to be. The tip is just let it dry overnight. It will get rid of all the water. It'll become a powder again. And then you just could just hoover it up or, yeah. So there we go. Anyway, speaking of someone whose house has been trashed by 12 months of lockdown by two small kids. Most of my job is clearing up at night. I'm like a sort of womble. I actually have turned into a bit of a womble. There's 2 hours of every evening that involves me wombling around the flat. Anyway, show and tell. So here. Can
I just say, Mark, you definitely have, I would say now, the delivery of someone who's at the end of their tether. There's there's a kind of Stockholm syndrome's the wrong way of putting it. It's not Stockholm syndrome, but it is that kind of I've just been trapped and these things have been going on. You can just dry it up, and then just hoover it up. Imagine, when do I get out? When do I get out? There's a nice kind of there's an urgency to you, which I've not seen before. Even when you went into the Royal Institute on that penny farthing, finding out that the door was a little bit too low.
I know, that was a disastrous moment, but I survived, and it only cost me my hair. My teeth are intact, though. And Robin, I reiterate what you said about teeth, which is when you're young, you sort of think, oh, that's fine, isn't it? Everything grows back, and I'm totally indestructible. And then as you get older, you think, I just wish I'd listened to those people who said wash them twice a day. I just wish I'd listened. I know it was cool not to wash them, but anyway. On the material science front, teeth, talking of teeth, here is a little bit of a show and tell. I saw this on my dad's desk every time I would wander in there and would not be shooed out. And it always fascinated me, and my eyes were drawn to it. And it's a really beautiful example of quartz crystals, but enormous ones. If you've got a watch or anything like that, you've got them inside that watch probably, but that's what they keep watches going. But it's just beautiful, isn't it? And it's what people think of when they think of as a crystal, isn't it? That's a crystal. And in some ways you think, well, it's a crystal, it's beautiful, but it's inanimate, right? So this stuff is like stone, beautiful stone, but it's stone. And but then when you think of animate stuff, or at least a living stuff, you think of something like this on this side. I've chosen the sides of the screen, by the way, on purpose. This is not random. And that is a little seedling which is growing, and that is harvesting energy from the sun. So better, in a more sophisticated way than we can as humans. And it's living, and if I break off a leaf, it'll regrow, and if I damage it, it'll heal itself. And it can do all sorts of things that we material scientists can't do, and we feel jealous. We'd like to be able to do that. But what
when you're rumbling around the flat at night, Mark, the plant's talking to you.
That's right. And what we'd like to do, this is the sort of big picture stuff, is we'd like to get somewhere in between. We would like to have something that's more alive, a bit more living like a plant, and a bit less dead, although beautiful like a crystal. And our progress so far as material scientists has been this in the middle. And this is a mobile phone. And really, I mean, it is an amazing triumph of material science. There's a touch screen, and it knows you've touched it. And actually, your touch, human touch, it can distinguish between human touch and other touches. So that's pretty cool. And it will communicate that right down to the nanoscale. So inside the material, that touch is distilled down into a bit of ones and zeros, and then a little silicon chip, which is another material science amazing thing, turns it to some idea of what they should do, and then it displays something on the screen, or it phones your mum, especially today. And that's incredible, but it isn't as incredible as we want it to be. It's not like over here, because it doesn't generate its own energy. When it's damaged, it doesn't heal itself, and it doesn't. Yeah, it's just not as cool as living stuff. So this is where we want to go with material science, that way. Have I said enough?
That's perfect. Thank you so much. And also, it's just one step away from you being the mad scientist in the mutations. I don't know if you've seen that film in which Donald Pleasance tries to splice human DNA with plant DNA so that we can all photosynthesize. And it doesn't go well. It does not go well.
You know what, though? Sloths can photosynthesize, but that's because they've got algae on their fur. So they just have algae on the outside. So maybe if Mark hadn't cleaned his teeth or he'd let algae grow on them, he would have photosynthetic teeth. That'd be quite cool.
Also, Donald Pleasance need not have killed all those people in those experiments. He could have just made a coat for someone. So it sounds to me like there's been a lot of issues in the 1970s horror science crossover world. Let's start off. Helen, I'm going to throw this at you first of all. This is Stephen Bamforth. He wants to know, why does all the washing end up in the duvet cover when using the washing machine or dryer?
It's a really good question, and I don't know the answer. It's really interesting, isn't it? I suspect it's because of a probability thing that means it may or may not get through the entrance, but once it's in, it's very hard for it to get out. So I suspect it's something like the equivalent of having a cliff with someone staggering about on top of the cliff, that they can stagger about up here. Eventually, they will stagger off the cliff, and once they've fallen off, they're not coming back up. So I don't know, but I suspect it's something like that. I have seen something similar with things like fish traps actually have so there are native communities in the Caribbean who have very traditional fish traps, and the traps have holes in them everywhere. There is nothing to stop the fish swimming out, but because of the way the fish navigate, once they've swum in, they just don't swim out. Some species do, but most of them don't. So I suspect that that's what it is, but I don't know. It would be great to know. It would be quite hard to get a camera. It'd be quite hard to do the motion tracking for that to find out. I have to have a think about how you do that experiment, but I don't know the exact answer.
Well, I'll throw this over with either Suze or Mark. Would either of you like to answer this?
I mean, I think it's amazing. It's an amazing thought experiment, isn't it? How does it happen? I think it's a great question. It's one of those fantastic science questions. So one of the ones you used to have at the back of the New Scientist magazine, isn't it? And loads of people would write in later on. But there's two bits to a washing machine, aren't there? If we just think it through, there's the bit where there's the water coming in, and so things are floating around different densities. I mean, I say floating, but kind of mashing around each other. And then there's the bit where all the water's gone, and there's a drum, and that gets the centrifugal force pulls everything out. And I should imagine that's not the bit where they go in. I should imagine it's the bit where the different densities are floating around. That's all I've got to add.
Yeah, I'd probably answer that actually, and just sort of say, I suppose float in, once they're being thrown about towards the edges of this drum, it's that much harder for them to escape because they're all kind of subject to the same kinds of forces. So they're kind of, I suppose, acting as one mass by that point. So it is annoying. I'm keen to kind of maybe work with Helen and Mark on creating an experiment for this, though.
Well, we can start.
It'll be fascinating to track them.
We can see how we start, right? Because your first kind of headline, just see what's going on experiment, would be to find, like, to basically stop the washing cycle at different points. Stop it after 5 minutes, stop it after 10 minutes, see what got in there first, see when it got in there during the wash cycle, and that would help perhaps guide future experiments. So I can see a starting point for this, although draining full washing machines tends to...
it's actually really hard to stop a washing machine and let it open the door. I've actually had that problem in the past where my washing machine went wrong and it's still half done, and you actually can't get it open. There's a very probably important anti-child look device that stops a little child come and go, oh, I don't know. So I looked online for for the emergency override, and it's not very easy to find.
There's a drain.
It can be overcome.
There's an artificial drain. You can drain it out yourself if you turn the power off and just open the artificial drain.
There is a simpler solution, of course, though. We could just button back up our duvet covers before we put them in.
You've got the button ones, eh? You haven't got the Velcro.
Yeah. Oh, no.
You don't need to use a washing machine, do you? If we can just make we just need a drum. So if we get a drum rather than use the washing machine, we can still create the same experiment without destroying all of this Zanussi technology. And also, don't use fish.
You have to destroy things, Robin. That's why we're all in.
Oh, yeah, I forget about that. So when you gave your warning about oobleck, we should be clear. Most of you don't need that warning about oobleck. It's just the way that Helen makes oobleck that creates this disaster. This is, right, let's go on to carbon nanotubes. Straight from duvets to carbon nanotubes. And this is S. Faber would just like to know, Suze, whatever happened to carbon nanotubes?
Whatever happened to them? They've been around for as long as we've had things like fires. A sooty fire is kind of full of carbon nanotubes and tiny cage structures called buckyballs and other kinds of what we call fullerenes. They've been around all the time. It's amazing, actually. There's an incredible history of things like carbon nanotubes and other nanostructures. There are particular swords that were made way back in the day, and they were kind of heated over these very smoky fires, and they were incredibly light and incredibly tough. And nobody really knew until a lot later when we started to analyze these things that the reason that these properties existed were because these carbon nanotubes from very sooty fires had infused within the iron or the steel that they were creating. And so we kind of learn from that. And we have been still using carbon nanotubes in a range of ways in reinforcing tires, all kinds of things. Tennis rackets, I think, still have carbon nanotubes that strengthen them. And they kind of dampen down a lot of the reverberation that you feel when you're playing tennis. But of course, they're incredibly light as well. So they're not adding a whole load of bulk. So they're keeping your game on top form. I think one of the most exciting ways that we're looking at using carbon nanotubes and these cage structures at the moment are things like targeted drug delivery. So if you think of a carbon nanotube, and I learned this from Mark actually way back in the day, you can kind of think of carbon nanotubes if you cap the ends as almost teeny tiny test tubes or little capsules, little vehicles. And if you add a range of markers on the outside of this that corresponds to perhaps different parts of the body, particular cells in the body, and you fill the carbon nanotubes with very specific medicines. Think about something like cancer treatment. At the moment, we look at chemotherapy and radiotherapy. You're treating all of the good cells as well as the bad in exactly the same way. And so by creating these tiny capsules that have these markers, you can set off these little vessels, these carbon nanotube carriers into the body. And when the markers reach their corresponding tissue, cell, whatever, they can then open out and they deliver the medicine exactly where it's needed. And you have this very targeted way of obliterating things like bad cells, like cancerous cells. So carbon nanotubes are still there. Carbon itself and carbon nanostructures are constantly being discovered. There's lots of new versions of nanocarbon that we're discovering, loads of different allotropes of carbon, all with these amazing different properties. So it hasn't gone anywhere. It's still about. And there's a whole load of future around carbon nanotubes and the technology that we can use even now.
Wonderful. That was like that moment when in Spinal Tap. Spinal Tap, they're currently in the where are they now category. But turns out not carbon nanotubes. So, right, this is for you, Mark. This is from Joe, who's aged 8. And Joe wants to know, is jelly a liquid or a solid?
Very good question. What is a liquid? That is the first thing we need to establish here, isn't it? How do we define a liquid? It turns out that's not so easy to do. Although solids are very recognizable, we saw one earlier. The liquid form of quartz or any other sort of liquid is one of the characteristics of defining a liquid is that it will fill a container. It will and assume the shape of that container. So if I was to try and put this bit of quartz into this cup, it doesn't flow into the cup and make the shape of a cup, and won't do for, well, pretty much ever. Although it will flow at very small rates, depending on the temperature. But other solid things that look solid will flow into them, and So you have things that are kind of very viscous, like tar. So I could get a lump of tar. I haven't got one here. That's bad. But you could put a lump of tar from the road. You could put it on top of this cup. It wouldn't flow immediately, but then over a period of months, it would actually flow into the cup, and it would fill the cup and make the shape of the cup. And so tar counts as a liquid, even though you obviously look at the roads and think they're covered with solid. So that is probably where you're coming from with this question, isn't it? Because everyone knows that jelly is pretty much a solid, and it wobbles, but that's because it's very has a low elasticity. If we put a bit of jelly on top of this cup, question, would it flow into the cup and make the shape of the cup? Answer, I think it would. I haven't done the experiment. And I think the reason it would is because actually what jelly is mostly water with small fibers which hold the water together. What's that stuff called? Gelatin, yeah. And so it's the gelatin fibers that are sticking all the water together. And when it sets, it's basically trapped all the free water. But that doesn't mean that these fibers can't move about and flow. And I think they would flow together and then they would reform again. So I think we can say that jelly is a liquid.
See, I think Joe's asking this. It's some kind of pudding argument. Come on, Mum. Surely I can have a pudding because jelly is only a drink and does not count as a full dessert. Dad, I'm telling you, I spoke to a man. Definitely, I've only had a drink. So let's find out. Thank you for that question, Joe.
We should just probably add, just on Mark's office, in Mark's office, when we were allowed to go to offices about a year ago, he's got bitumen and it's dripping, and it's been, I don't know how many years it's been there for, but maybe you could describe it, Mark, because it's probably dripped quite a lot in the years since you last saw it. But maybe you could add some jelly to that shelf.
Yeah, I should add some jelly. I've got a piece of bitumen which I got from a road builder about the size of this kettle. Don't ask me why kettle's right next to my laptop. But and I put it on a shelf and it sat there for a few months just being bitumen, a lump-like. And then 1 year went by and it sort of slumped a bit. And then another year went by and it started to drip off the shelf. And every time I'd have tutorials, you'd see the students' eyes would dart over into the corner and look slightly nervous. It does make you feel slightly uneasy about the world, that the roads might just drip off and that buildings might sort of flow into a big pool into the muddle in the floor.
But it might have dripped. You know that drip that they had in Australia? They waited 20 years to catch it. It might have dripped while we've been away from campus.
The 10th drip.
Yeah.
But that's why he's a womble, because sometimes he goes and he finds some bitumen and it just goes off with him. It's fine. This is a question for you, Helen, I think definitely, because it's from Michaela S.'s daughter. And she would like to know, why are bubbles just round? Why are bubbles always round?
Oh, well, they're not. But so soap, there's different types of bubbles. That's thing number one here. So soap bubbles are ones where you have air inside and then a layer of liquid and then air on the outside. But you also have underwater bubbles, which are just water inside, a gas inside a liquid. Mostly the reason that small bubbles are spheres is that there is an energy cost to having a surface. And if you want to minimize that energy cost, you make that surface as small as possible. And if you do that, you end up with a sphere. So one way to think about that is it's as if there was an elastic skin coating the bubble, which is the way that surface tension behaves. And in the same way that a balloon is round, mostly, it will pull on itself until that pull is equal everywhere, and that pulls it into a round shape. However, soap bubbles are very easy to disturb from being, and underwater bubbles, you can squish them. You can, if you blow very gently at a bubble, you'll see it deform. So it's only ever a sphere once you've left it alone, when there's nothing else happening to it and all the forces are balanced. But actually the skin, it's not like a fixed skin that only has a fixed size. So it can extend and it can be sheared, and it can make all kinds of lovely wobbly shapes. So it doesn't, so they're only spherical if you leave them completely alone. And technically, on a planet with gravity, they are never perfectly spherical, because the water inside a soap bubble will drain down to the bottom. And so almost always, if you blow a soap bubble and you see it drift away, this happens too quickly for you to see, but it'll pop at the top. because that's the thinnest bit, and the water has all drained down to the bottom. So even if you really, really zoom in, that even the gravity will stop them being perfectly spherical. So the only place you could have a genuinely properly spherical bubble of that type is on the International Space Station, or there are things called anti-bubbles, which you can make underwater, which are spheres to a very, very close approximation. But of course, because they are a drop of liquid surrounded by a layer of gas with the water outside, after a while the air moves around to the top, so they pop from the bottom. But they're spherical for a little bit longer than a soap bubble. So yes, that is because they're trying to minimize their surface.
I hope that was, I think, an excellent answer there for Michaela S.'s daughter. Now, this is a very interesting one, because this is from Nick F., who says, how small can things get? What is the smallest thing there can be? Can things be infinitely small? Now, I presume that there is a point where we move from the model of the universe that is the one that we kind of experience to then a quantum situation where definitions change. But I don't know. So, Suze, can I start with you on this?
Yeah, you can certainly start with me. So without delving too far into the realms of sort of subatomic physics, I would probably class the smallest thing. People will get angry, won't they? The physicists always like to get angry. I apologize. In my world, I would say probably the smallest thing would be a hydrogen atom. So a hydrogen is the smallest atom on the periodic table. This is the smallest, lightest element, and an atom is literally just a happy little proton with an electron going around it. That for me would be the smallest thing. If we talk about things around us, hydrogen atoms themselves kind of don't necessarily exist happily on their own, because they like to form diatomic molecules. So you have your H2 molecules. But I would probably say, without delving into the world of subatomics, a hydrogen atom would be the smallest for me and my definition of things existing.
You don't like the old proton, do you? Then I mean, the proton.
Well,
I mean, is that subatomic? I mean, I guess it is it's a charged atom, isn't it?
Mm.
But this is all. I mean, that you do get into this. The protons are made of this, and then and in the end you end down at the quark stage, don't you? So you keep going down. There are all these little subatomic particles, down and down and down you go, and then all the matter that we know exists, the visible matter, which is only 5% of the universe, as I understand it, is made of quarks. And then in their behavior, or to go smaller than a quark, we have the Higgs boson, right? That was the thing. That was the whole Higgs boson.
Well, then there's
this is kind of my. Go on, Helen.
There are other gluons. So I think once you get, then you get into this territory of exchanging particles to give things properties.
This is my argument, that these things I don't think can be defined as existing without the existence of relevance, meaning, context, something that they can kind of be up against. So that's why I think we can't necessarily count subatomics as the smallest things. But I will take you on a hydrogen ion, a proton. I'll consider that.
What's a great there? Because my connection went for about 3 minutes, and I just got to your summary, and I just got to you saying, and that's why. And now I won't know.
We just thought you were listening very, very intently.
Always. Sorry, Mark, you wanted to add something there.
No, I'm just saying that I think philosophically, I'm not so interested in small things. That's me, because I think that I'm not of the opinion that the smaller things are, the more important they are to cause the rest of the universe. Like I never bought that argument. Like all the scales of matter talk to each other. They all interact with each other. So it's exactly, I think, Suze's point really, which is that you can't have small things unless you have big things, and so it's basically a continuum, even though we have quantum mechanics, which is the rules of the small stuff continuum. We also have the big stuff and relativity, and the fact that we haven't really worked out how to match those two theories is I think fantastic, because science is about asking interesting questions. But I suspect everything's infinitely small. I suspect there is no. It's the only satisfying explanation to me.
But that's actually why Susie's answer is a good one, because actually the size of a size of a hydrogen atom is defined by the distance between, like it's a spatial thing between the proton and the electron cloud around it, and so it's not about a thing. It's actually about the relationship between two things, and that's what gives you size. It's the relationship between two things, not one thing on its own.
I know
that's so coherent, Helen. Yes.
But you do get sometimes a little bit frustrated, don't you, Helen, with people non-scientists, the obsession with people always reading books about quantum physics and kind of becoming immersed in it, and sometimes missing out on it, because it is an interesting thing, which I found. I've done that. I've got a huge stack of books about quantum mechanics, and if I'm really honest, I would say the amount that I've learned per page is probably one of the smallest. I suppose it should be the smallest amount, but you know what I mean. That's not meant to sound kind of fun, which is
that it is unit of anything is. There you go.
Yeah.
To be really rude to some quantum mechanics people.
Yeah, and that's a whole discussion. We'll get to. There's from Andy Pickering. Thank you, Andy, for your question, and thank you for all your support. Andy is a very regular supporter of Cosmic Shambles. He would like to know, how much does heat conduction from the Earth's core contribute to weather/climate, and is it very gradually reducing? Helen.
Yeah, I do know the stats on that, because I get asked this quite a lot because, well, I look it up because I know there are pedants out there, which is so people say, because I use phrases that say things like basically all of Earth's energy comes from the sun. And somebody always says, but what about radioactivity from the core of the Earth? And you can actually do a budget for the energy, the entire energy budget of Earth. And quite a lot of it, on average per square meter, 343 watts per square meter comes from the sun, and it's radiated away at half a watt per square meter less, which is climate change. But anyway, but then there's this massive reservoir of energy in the Earth system. And then there is a tiny, tiny amount from tidal heating, which is sort of stretching and squishing, just, because the moon moves the tides and the tides cause friction, that generates a tiny amount of heat. And geothermal heating, which is due to radiation, large atoms decaying into smaller ones that releases a bit of heat. And the fraction of energy that is due to tidal heating and the geothermal energy as a fraction of the total Earth energy budget is minuscule. I can't remember the numbers, I've got them somewhere, but it's something like 0.0001% of Earth's entire energy. So yes, in theory, energy is coming from those sources, and it is dissipating with time. The moon is getting further away, so the tides were decreasing ever so slightly. Once radioactive atoms have decayed, they don't go back the other way. So you're running down a limited supply. But the timescales that's happening on are really small, and the contribution is very, very tiny on our planet. However, there are moons out in the solar system and planets themselves where tidal heating and radioactive decay are, especially tidal heat, actually really, really important. So for our energy budget, minuscule, but for other things out in space, can be quite significant.
Thank you. Suze, this is from Beowulf42, and Beowulf was looking at a video of water polymers that was trending on Reddit this week. The bit that really freaked me out was when someone placed one from their hand into a clear bowl of water that was then shown to be full of other previously invisible water polymer balls. The question is, what? Why?
This all comes down to what's known as the refractive index. We talked about things interacting with light earlier when we were talking about butterfly wings. Everything has a refractive index. It's a measure of how something interacts with light. And if you have two materials that have the same refractive index, they're indistinguishable from one another. The thing with these water polymers is that they're actually hydrogels. So they're usually made of sodium polyacrylate, which is the same stuff that you get in nappies. And the reason that they are these hydrogels is because they suck up loads of water in this kind of network of polymers, a bit like the jelly that Mark described earlier. It's this network of very long chain molecules, and in between all of these pockets, they can accommodate lots and lots of water. If they haven't been soaked in water, they're these teeny tiny, almost glassy beads. They're quite kind of brittle, they bounce. That's quite different to how they end up being. They swell to many times their original size as they suck up all the water. But the thing is, because they're almost so closely they're basically mostly water, which is why, particularly when you put them in water, you have the same refractive index. They're indistinguishable. You can do this with other materials. One of my favorites, I don't have the showmanship of my husband, but my husband does this beautiful demo where he will take a piece of Pyrex and he will embed it in a big beaker of glycerol, and it just disappears. So you can just see the markings on it, but the actual kind of the smaller vessel will disappear into the glycerol, and then you take it back out again, and of course you can see it, but usually he's embedded several other pieces of Pyrex glassware in there, and so you can then take them all out, and it's very magical and beautiful because it's like you're creating something from nothing. But the only way that works is because the glycerol and the Pyrex have the same refractive index, and so you can't effectively see one in the other because light is interacting with them in very much a similar kind of a way. So the light is kind of passing through them and reflecting in exactly the same way.
But there's a really interesting corollary to that, which is that we can't see Pyrex at all. What we see is light doing weird things because there's Pyrex there. So it's not like light hits Pyrex and it changes color and then bounces back, like with lots of other things. You see reflections of things. You see places where the light's been bent. You can't actually see the Pyrex itself. Which is why when you embed it in something where you take all of those effects away, you actually can't see it, and you can't. So it's a really interesting thing about glass in general. Same with bubbles. You can't see a bubble. You can only see the way it messes with the light field around it.
Fantastic. Thank you. Hello, everyone. By the way, you're watching Sunday Science Q&A. We're here every Sunday. Next week, Nicole Stott, who is astronaut, engineer and artist. And don't forget, you can also support us via patreon.com/Cosmic Shambles. And our current tips for existence is Tim Minchin. Had a very nice conversation with Tim Minchin. And next week, the tip for existence is Francesca Stavrokopoulou. Now, this is a question from Jamal. We're going to move slightly beyond jelly now, Mark, but get ready for this. This is, why are some solids harder than other solids?
Right. Yes. Good one. So solids are states of matter that all the atoms, or most of the atoms, are bonded together with their nearest neighbors. And so hardness is essentially defined by how much, if you can easily move them apart at the surface, so scratch them. So when you scratch something, essentially you are physically getting some of the atoms at the surface and you're sort of pulling them apart from each other, right? You can think of them as breaking a bond there. So here's two atoms at the surface of a solid. They're bonded together by some sort of bonding, and now you're doing something to pull them apart. So that's definition. How much energy does it take you to do that as hardness? And so that depends on how strong that bond is, really, and also how much energy it takes to sort of put these atoms to push past their neighbors. So in the case of metals, that's done via dislocations, which are a particular mechanism in crystals that allow whole bits of the crystal to shuffle away from each other. And that's why metals are so useful, because they're both hard, but when you put that scratch in it, it doesn't fracture the whole thing. So why are some metals harder than others, or some materials harder than others? It's essentially to do with how strong those bonds are.
Thank you,
a very
Mark.
soft thing. Oh, okay. Well, that's
no. Please go.
Well, a very soft thing, has very soft bonds, and so chewing gum and that sort of thing, and jelly. In fact, the bonds holding all those things together are Van der Waals bonds, which are very very weak bonds, and then you have a very hard thing. What's the hardest thing in the world? That's a good question. So things like silicon nitride. And as a particular crystal structure of carbon. What's it called?
Is it tungsten carbide or something?
Well, tungsten carbide is very hard, but there's an even stronger bond. Anyway, it'll come to me. But yeah, and you can only find it in meteorites that come from outer space. This particular bond, Lonsdaleite. I am not that old. I can remember stuff. Okay, good. That was a good moment for me. Thanks for asking that question.
Uncle Bulgaria, you've still got it. Elizabeth G. Now, it's similar, I suppose, to whatever happened to carbon nanotubes. Elizabeth G. would like to know, she said, I remember when graphene was first announced, it was done so claiming it would change the world forever, but I don't heard much about it since. So, Suze, what is going on in the world of graphene and the way it is being used?
Graphene, yeah. So I am a fan of graphene. Graphene, if you don't know, is it's graphite, but it's basically one sheet of graphite. So it's one layer of carbon atoms forming in this continuous sheet. And it's very exciting. It can conduct heat and electricity incredibly efficiently. It's transparent. It's flexible. It's so strong. But it's not currently super useful. It can be used for things like very small electronics, and that's all being developed further at the moment. But the problem is, because it is so thin and it's so hard to work with, using graphene itself as this, what is a two-dimensional material, because it doesn't have any other atom layers to it, it's pretty hard. So I know that the Graphene Centre up in Manchester have expanded the definition, and material scientists generally have expanded the definition of graphenes, and that is plural. So we take a few layers of graphene to still be a graphene-like material, but particularly it's now being used as a more kind of analogous term, where lots of other kind of two-dimensional or single atom materials are being created. So you can actually get a few alloys that do some amazing things, and they're just a little bit easier to work with. So graphene still exists. I think graphene is one of those materials that's going to find its place, and graphene type materials, as they sort of stand on their own, well, 2 feet, I was going to say, but on their own single atom layers. But I think that the real beauty, particularly in material science, is very much this Avengers Assemble attitude, where a lot of these nanomaterials can be embedded in other materials, in composites, where we can retain a lot of the properties of these initial different materials, combine them together, and you get something that's actually a little bit more useful, a little bit easier to handle, and it can be used in a range of different applications. So graphene's still there. I do feel like a lot of this is, hang on, we heard about nanotech a while back. What's happened to all this stuff? It's still there, and there's still loads of research going on around it. But I think particularly in material science, it's not just the poking and the prodding of the science, but it's actually finding useful ways of applying it. And I think a lot of those ways do end up, it's such a beautiful analogy for research, that basically by collaborating, you achieve more and you're able to do more. So yeah, graphene's still there, but it's mostly at the moment in other things and inspiring new research.
Right, just to warn you, the next question you're going to get is going to be about nanobots and how they can possibly be used by Bill Gates in vaccines.
I'm ready.
We'll give you a little bit of a pause before that, because I'm going to ask you something.
Can I ask Susie something about this? Because I remember something coming up a couple of years ago about this. I think it's graphene oxide. There's a particular pore size in that you can engineer that will let water through, water molecules, but nothing else.
Nanoporous kind of filtration
opportunity for desalination, and we know that a technology for desalination of water, a cheap one, low energy one, will be life changing for so many parts of the world. And that was the last thing I heard about it. I don't know if you've heard any more. I mean, it was one of those things in the lab, so I don't know.
So there is nanoporous filtration. So as you say, people can effectively you can not really punch holes through it, but chemically induce holes that are of analogous size to a water molecule. So everything else is held back, but a water molecule can pass through. So it's good for desalination. It's good for things like conservation efforts to try and clean up oil spills and things like that. Oil, is made up of very, very long, very large molecules. So it can be used for that. Graphene is even being used in things like batteries to house lithium ions in a kind of almost egg carton-like way. So there are kind of lots of ways that it can be used, but I think graphene is this kind of continuous sheet, which is what people mostly see it as. It's not finding as many it is finding uses. I think it's unfair to say that, but it's just with anything that's nano-scaled, scaling anything up is always a big challenge. So it can work on a really tiny scale, but as soon as you start to build it up, it loses a lot of those properties. It loses the kind of commercial scalability as well. So I think in that case, graphene's still trying to find its way. But yeah, the nanoporous stuff is incredible.
Thank you. And we've got 10 minutes left. Let's see how many more we can get through. This is for you, Mark. Annabelle has been watching a video of you at the Royal Society talking about adaptive materials and self-healing paint. And she wondered if you might be able to explain a little bit of the science of those ideas.
Well, so this is the animate materials I started with. The idea, so self-healing is one of the features of materials we'd really like to have in more materials. Imagine a bridge that knows it's cracked and can heal itself. It's a particularly useful application, or an aircraft wing, or your phone screen. So, I mean, the idea that materials could have that capability seems far-fetched, but actually we already have materials that are doing it, and they work in several different ways. So there's paints out there. If you get a high-end sports car now, you can buy a self-healing paint, and that, if it gets scratched, then over a few days in the sun, that paint will get rid of that scratch. And it does it really by a sort of surface tension effect. It's kind of it's getting energy from the environment, and it's allowing the paint to flow back into the cracks. The self-healing concrete, which sounds really useful, doesn't it? And it's on the market. It's a slight cheat because, well, what do I mean by that? I mean that the mechanisms by which it does it are add-ons that are quite difficult to engineer. One is a bacteria which is embedded into the concrete, and it remains dormant for 50 years unless a crack opens up, and then it smells the kind of damp air, if it is damp, and wakes up, and it starts eating, because the concrete manufacturers have left little packets of starch in it, and so it eats those up, delicious, and then it has a poo, and the poo is calcite, which is one of the major constituents of concrete. And then it keeps eating and pooing and exponentially increasing in number as bacteria do, until it reaches the edge of the material, and it's left pristine material behind it. So it's healed the crack, and then it reaches the edge, and there is no more food. So the concrete manufacturers do not leave food outside it, and then they all die. And that ethical issue around the self-healing concrete is something we're still grappling with in material science, whether that is an unfair...
I've now got this terrible mental image, though, of bacteria that go the wrong way and go on eating and pooing and lock themselves and build themselves a prison cell.
Yes, or start building a bridge themselves. They go, hey, we don't want to go this way, we want to go that way. And that's some of the ethical issues we have been dealing with in the report from the Royal Society, which we launched last week. And if anyone's interested more in this topic, because we actually have collated well, not all, but many examples about these different amazing smart materials and active and what we call them animate materials. Please do look up the Royal Society report on animate materials, because I think you'll enjoy it.
That selfie thing just gave me images of Stephen King's Christine, so that worried me a great deal. This is, well, I'm going to get onto the nanobots in the vaccines, Suze, because this is such a, and this came up the other day. I think it was Naomi Wolf's account mentioned this idea of it said nanoparticles. I don't know if it was actually nanoparticles. It might have just been a typo, and about the idea of time traveling, which again started to make me think, well, maybe if you get down to a certain size, again, quantum size, where, yeah. Anyway, so this is the question from Mark is, are these sort of nanobots that we're hearing about, or controllable nanoparticles, actually possible in the way that perhaps you would read about them in Michael Crichton's fictional book, Prey?
Sure, I've been gifting everybody nanobots for Christmas for many years now. They love them. No, so nanobots are a really interesting thing. It's one of the many things that are born from a lot of science fiction ideas. And we know that science fiction inspires a lot of science fact, and that's great. The funny thing is, I think the closest thing that we have to what we would consider a nanobot at the moment is any kind of virus. So viruses are incredible in that they go about their business with a tiny bit of coding, they follow instructions, and they happily go about their business. There are ways that certainly kind of biochemical engineers are looking to engineer viruses to do good things. But the idea that we're going to have kind of, and the nanobot argument has come up in a pandemic that is being fueled by an incredibly clever virus itself. So it's kind of a funny one. Nanobots there are ways that we can engineer these kind of viruses, the closest thing that we have to nanobots, to start to create materials, to a kind of bespoke instruction. So we're looking at things that can kind of assemble themselves in a way that we would like. They're probably the closest thing that nanochemists and nanomaterial scientists have to engineering things on a kind of atomic or molecular level. But are we there yet? Not quite yet. You may have seen some kind of videos and things that do the rounds now and again of viruses or very small kind of virus-like, or even clever molecules that can be engineered to do very specific things. Molecules are, I suppose, one way that we could start to think about nanobots. If you start to create molecules, for example, that have specific charges on different ends that mean that they're going to interact with materials in certain ways. I'm thinking of the one where there's this meme that does the rounds every now and again, and it basically looks like something that's walking along on this really teeny tiny scale. You can kind of think of those as, it depends on how you define a nanobot. In terms of the sci-fi aspect of it, no, probably not. But viruses are probably a very good contender to do good things, rather than things that are not ideal, that have, the whole world locked down in a pandemic. And potentially kind of using engineering skills and nano-engineering skills to engineer molecules that can do certain things. I know Mark has done a bit on self-assembly stuff as well, and this kind of feeds into a lot of your self-healing and self-assembly work. So I don't know if you want to pick that one up.
No, you don't, Mark, because we've got too many questions, only 3 minutes left. Helen, I'm going to throw this to you very quickly, which is, you mentioned the other week that bamboo-based clothing is not good for the environment, and John just wondered, why is that, and what are the better options?
Oh, so my beef with bamboo-based clothing is that the problem is, so you use a feedstock, which is a natural cellulose, but then you basically turn it into something which is quite like most other plastics, which is rayon. And so the equivalent, and so my problem with it is that I think if you make a bike out of bamboo and all the struts are pieces of bamboo, that biodegrades, and that is great. But if you use bamboo feedstock to make something that's quite like a normal polymer, and we found a lot of that in the ocean that hasn't biodegraded, then it's not as friendly as it sounds. It's not just bamboo. So my problem with it is that maybe you can justify doing it, and it's probably better using bamboo rather than oil. However, it is not true that it's automatically biodegradable after you've gone through these processes. So better things: cotton, linen, wool, anything that biodegrades, in my book.
Thank you. One for you, Mark, which is from Leanne. Leanne used to have one of those bracelets, which was a straight piece of kind of, it was like metal, and then you would slap it against your wrist and it would curl around, and so you would then have a bracelet, and then you could straighten it out again. And she wants to know, how did that work? What is it? I presume that's about the bonds,
cool.
or
so cool. So it's actually a bistable mechanical device, is what it is. So you piece of paper, right, stable like this, but it can also be stable like that. And so when you're slapping it round, it's going from one stable curvature to another one. And it just, you put enough energy in, you switch between the two, and they're both stable. So it switches from one mechanical stability to another. So cool. Love it. It's just
like
brilliant.
Hair clips, the little snappy hair clips, effectively do the same thing.
Yeah.
Wonderful. We've got time. So this is from Dylan. And this is photoelectrolysis for hydrogen fuel production in cars. Will it ever be possible on a wider scale? Let's make that a yes/no answer.
Yes, with work and co-catalysts that do it well. Yes, and efficient scale up, and an infrastructure that supports it. Yep.
Brilliant. Mark, would you like to add anything?
I don't know. Yes.
That's fine. Then let's go with an I don't know. That's absolutely fine. Eileen and David and Steve, we haven't had time for your questions. We will ask them next week. And especially David, your one. And also, in fact, we haven't got time for Steve's. I'm so sorry, Steve, but I know you, so it's okay. Thanks very much for listening. Thanks to Suze and Mark and Helen as usual. As I said, next week we've got Nicole Stott. So engineering, space exploration, so many things. It's a really wonderful like so many of our guests, a real polymath. And I'll just quickly mention as well, if there's a blog post that I've put up on Cosmic Shambles about why I decided not to do an event at the Science Museum recently, down to BP, etc. sponsorship. And if you want to have a look at that and see, you may well entirely disagree with my reasoning for it, but that's up at cosmicshambles.com. And also Tim Minchin on our Tips for Existence, and the new Uncanny Hour, Derek Jarman and Jubilee, and Book Shambles, and loads of other stuff. Go to cosmicshambles.com. You'll see all those things. Thank you very much to our producer, Trent Burton. Thank you very much to Helen, who we will see again next Sunday. And I hope you enjoy the rest of your Sunday and the rest of your week. Bye-bye.